Hello everybody, today is Thursday, March 19th, and we are starting on another section for our transformations chapter, and that's going to be vectors. And you guys are going to like this section because it takes a little bit of last chapter and combines it with this chapter, and there's not as much work as there is in other sections of transformation. So let's look at our agenda for today. Today, you would have watched the agenda video to identify all your tasks for today. You should have completed the warm-up that is posted to Google Classroom. You are currently watching the video for vector notes. And then you have a short little My Math Lab assignment. And all this is due by midnight tonight. So if you have any questions, I can't spell any. If you have nay questions, okay, please email me. All right, so what is a vector? Well, it's going to be bringing back some of that coordinate plane action that we are starting with transformations. And a vector is described as any quantity with a magnitude, a size, and direction. That's the most basic definition for a vector. You will most commonly visualize it as that image in the upper left corner. It typically appears as a line segment with an arrowhead on one end, okay? And it's describing the movement from one portion of the coordinate plane to another. So within this chapter, you can draw vectors between your pre-image and image to describe that movement. That's why it's kind of tucked into this chapter. But a lot of times when we have our vectors to identify our horizontal and vertical change, we'll use Pythagorean theorem. You'll use trig. So typically this is kind of like the stepping stone in between each chapter. It's kind of in a funky location because yes, we use it to describe transformations, but today all we will be doing is Pythagorean theorem and trig. All right, so what is magnitude? Magnitude is going to be size. It's that distance between your initial point, your starting point, to your terminal point, ending point. So terminal, think like at an airport. It's your last destination before you get on the plane. That is your ending point. A vector is represented in a coordinate plane with an arrow drawn from your initial point to your terminal point. And vectors are written as, for example, PQ with kind of like that half arrowhead above it, but we read it as vector PQ. How we describe vectors, we use component form. So if we were to write a relationship for vector PQ, we would say, okay, vector PQ is equal to A comma B with my alligator signs around it. What is that A and B? A is going to be that horizontal component or your change in X. And B is going to be that vertical component or your change in Y. So it kind of brings a little bit back of algebra, analyzing slope and your change along those segments. Okay, so let's look at this in practice. So example 1, describing a vector. We are given vector OL in our image, and we want to write the component form for OL. Well, we don't have our back grid for our vector, so I can't just sit there and count how many spaces it moves. However, though, when I look at this image, I see I have an angle, I have 50 degrees, and I have my hypotenuse. And because vectors are on a coordinate plane, we can typically draw imaginary lines to make it a right angle. So I have a right triangle. I can't use Pythagorean theorem here because I don't know one of my sides. However, I can use my trig ratios. So if I were wanting to solve for x, starting at 50, I know adjacent and I know hypotenuse. So adjacent hypotenuse, SOHCAHTOA, TOA, it's going to be cosine. So cosine of 50 is equal to x over 65. So x is equal to 65 cosine of 50. X is equal to, let me type her in, 65 cosine of 50 That's going to give me 41.78, but I'm going to round that to 41.8. All right, there's my x. Now I need to solve for my y. Well, my y is opposite hypotenuse, SOHCAHTOA, so I'm going to use sine of 50 is equal to y over 65. Y is equal to 65 sine of 50. So let me tap her in. Y is equal to 49.79, so 49.8. So now I have my change in x and my change in y. I can write it in component form. So I'm going to add so I have vector OL is equal to 41.8, comma, 49.8. Now, that is wrong. This answer right here is wrong, but we can do something to make it right. So I want you to take a moment, look at that. Why is that wrong? Well, looking at what I've written right there, if I had a coordinate plane, and let's say my starting point was here, I'm wanting to draw a vector. Okay, I move positive 41 spaces to my x, all right? And I move 49 spaces positive. There's my vector. Does that look like our vector on our screen? No, it doesn't. Because, okay, here in my answer, I have two positive values. Well, on my graph, it shows me that I am moving along my y-axis. I'm moving down, so it will be negative. So I need to add a negative sign here to my 49. So if I were to go back and re-graph it, okay, I go 41 positive, 49 down. So my vector would be here. That is where you're most commonly going to make mistakes today. You may solve for your answer and get a positive value, but however, to really describe that relationship of the vector, you have to add those negative signs. So if your y value is going down, it's going to be negative. If your x value is going to the left, it's going to be negative. Okay? All right. To describe direction, we use a compass. So, hold on, I'm going to go back, make that smaller. Think back to our lovely phrase, never eat soggy waffles or soggy watermelon. I heard that one, which I don't know who's eating soggy watermelon because that just sounds disgusting. But I guess soggy waffles do too. Oh well. Okay. Here our question is, what's our direction of each vector using compass directions? All right. You are going to trace the path. So here, if I were wanting to describe in vector A, so let's look at A first. My vector is moving 25 degrees, okay? And I just have to describe its motion. Well, the two compass directions that I'm going to be concerning myself with is east and south. And typically when I'm describing a vector, I think of as if I'm giving someone directions on a street. Okay, where is Walmart? Well, Walmart is 2 blocks past Target. Well, think of it here. If I were describing this vector would be 25 degrees. What direction did that move? Well, it moved south. So it's 25 degrees south of where? Where did it move 25 degrees south? Well, it moved 25 degrees south from east. So when you're describing the direction of each vector, you identify, okay, how many degrees did it move? What direction did it move? And where did it come from? So this is how much, where it go, a little bit of broken English, and from where. Okay? Now move that down. Y'all, I'm becoming really fancy-dancy with this iPad drawing. I'm really proud of myself. Okay, let's try B. Pause this video, give it a try, then come back and check your answers. How much did I move? I moved 35 degrees. Where did it go? Well, I moved 35 degrees east. From where? North. Yay! Okay, not too shabby. All right. Our last example. Okay, this kind of involves a little bit of application. Vectors are used a lot in, how would I describe this? The airplane industry? Pilots, maybe? Okay, they use it to describe their location, as far as they have a coordinate grid that falls across the whole globe, and they describe their movement using vectors. So, here an airplane lands 40 kilometers west. If you notice, they gave this value a negative sign because it moved this way across the coordinate plane. It moved to the negative domain. However, if I was describing someone, okay, hey, drive 2 miles, I'm not going to say, hey, drive -2 miles. The reason we attach that negative sign on there is to describe its movement across a certain coordinate plane. All right? And I moved 25 kilometers south. Well, south is also going to be a negative value. This trip can be described by our vector of -40, -25. What is the approximate magnitude and direction of its flight vector? So I am wanting to solve for this value. Okay, I'm wanting my quote-unquote hypotenuse, and I'm also wanting to solve for my angle. How much did it move? Well, notice I have 2 legs and I have a right angle. So in order to solve y, I can use 2 things. I can use Pythagorean theorem. I could use trig ratios, okay? And there's also another form that the book demonstrates for you to use. It says to use distance formula, okay? Which would be a longer method. I don't prefer to do it that way because I can use Pythagorean theorem or trig ratios and it would be faster than typing it into the distance formula. But I want to demonstrate that to you just in case you need to use it. Well, to use it by distance formula, I would write these as coordinates. I would have -40, 0, and I would have 0, -25. And I would use those coordinates to solve for my distance. Okay. However, I think that's longer. So, and I prefer to use Pythagorean theorem and trig ratios. So to solve for y, I'm going to use -40 squared plus -25 squared equal to y squared. Let me grab my calculator. 40 times 40 gives me 1,600. Okay, 25 times 25 gives me plus 625 equal to y squared. Add those together, I get 2,225 equal y squared. When I take the square root, I get y is equal to 47 point, I'll do 2. Okay, I'll round that up. All right. There's my distance. Oh, wait. All my answers are rounded to the whole number, so I'm just going to lose my decimal. Okay? I have my distance, so it's not going to be C, it's not going to be D. So now I just need to solve for that angle. Well, I have an opposite and I have an adjacent, so I'm going to use tangent. Tangent of x is equal to 25 over 40. Oh, negative. Okay. Oh, whoa. Okay. I'm going to take the inverse, switch my -1, -4, switch my side measure and angle to solve for x. X is going to be, let me type her in, 32. So my airplane moved 47 kilometers at 32 degrees south of west. All right, that's it. That's it for today. So this was kind of like a shorter section, basically identifying what is vectors. Okay, how do we use it? How do we use it within, or more so that vectors. Today's lesson of vectors is kind of like that segue, that stepping stone in between last chapter and this chapter. Because today we did not analyze vectors in the use of translation, rotation, dilation, but we will dive into that in the next couple sections. So today's kind of like that base ground. Like if I were given vectors and I were wanting to describe my movement between certain points within my polygon and describe the transformation, I can do that. All right, so you have finished watching your vector notes. Your next step is to complete your My Math Lab assignment. If you have any questions, let me know. All this is due by midnight. Have a good day, guys.